Alright, so now we're going to do problem 92 from chapter 4. An astronaut is rotated in the horizontal centrifuge at a radius of 5 meters. So your R here is 5 meters. And what is the astronaut's speed if the centripetal acceleration has a magnitude of 7g? So your A here is 7g. And so you want to find the speed. Okay? And how many revolutions per minute are required to produce this acceleration? So revolution, and what is the period of the motion? So you want to find the velocity, the revolution, and also the periods. How do we do that? You're given this information. You have your R, you have your A. Remember, the centrifugal acceleration A is equal to V squared over R. So you have this 7g, so you have 7 times 9.8, and that's equal to V squared over your R value 5. So your V here can be easily calculated to be 18.5 meters per second. Okay? So once you have your velocity, you have your radius. We can calculate our periods because it's actually easier to do. So let's do that first. So period is equal to 2 pi r, the circumference, over the velocity. So you have your 2 pi, and then you have your r, and then you have your velocity. So you can calculate your t value. The period is 1.7 seconds. And then you also find the revolution. Now, in the lecture, we mentioned that, to find the revolution, then you just basically take the inverse of the periods. So what is the revolution? The revolution is equal to 1 over t. Now, because you're asked to find the revolution per minute, so the first thing you do is that change that to minutes. So it's 1.7 over 60, and that gives you minutes, okay? So you should have... So this value is about 0.0283 minutes. So we're going to plug in here. So you have 1 over 0.0283. So what you have here is that you get 35 revolution per minute. Okay? So you can see that this is a very straightforward problem. You're given the radius, you're given the acceleration. You just basically calculate the velocity using the expression for the centripetal acceleration, and use this. This is the standard equations for the circular motion. So you have 2 pi r over v. Then you got your t, and then take the inverse of the period. That gives you the revolution per minute. Okay, when the period is in units or minutes. All right, so moving on to the next problem. That's 111. And I'm going to erase this. All right, what is the magnitude? What is the magnitude of the centripetal acceleration of an object on Earth's equator due to the rotation of Earth? Okay, so you want to find acceleration that is that's for an object on the Earth equator due to the rotation of the Earth. And what will Earth's rotation period have to be for objects on the equator to have a centripetal acceleration of magnitude 9.8 meters per second? So you want to find what is t if the centripetal acceleration now has this value of 9.8. Okay, and so basically you can see that during the part A, we don't know the centripetal acceleration, but we do know the period of the Earth, right? So once you know the period of the Earth, because we know the rotation, it basically rotates like every 24 hours. So it's so you can actually use that. So let's see, how do we do this? So you have let's see, acceleration is v squared over r. So we need to know the radius of the Earth. We also need to know the speed of its rotation, right? And we know the period. So remember, period is equal to 2 pi r over v. So from here, you can actually calculate the velocity. And once you have the velocity and plug into this, you can calculate the acceleration based on the information of the Earth. Okay, so what is the So that's let's see, so that's to our v. So from this we know that the velocity for an object at the equator would be 2 pi r over t. And you have your 2 pi, and what is the radius of the Earth? The radius of the Earth from the back of the book is 6.337 times 10 to the 6 meters. So that's your 2 pi r, and then the period. The period of the Earth, 24 hours, so you have 24 hours, 60 minutes, and then 60 seconds. So you can calculate this. After you do the calculation, your V value is 463.2 meters per second. Okay? So this is the velocity of an object on Earth, and you don't really feel that because you are part of the, in this reference frame. So, but it is, you are moving at this. The object at the equator of the Earth is moving at this speed. Okay, so it is 463.2 meters per second. Once you have that, then we'll plug into this equation. So you have 463.2, you square it, and then you have your R values, 6.37 times 10 to the 6. So after you do the calculation, your acceleration, you should have a very small, centripetal acceleration, which is 0.0336 meters per second. Okay, so this is the magnitude that you calculate based on the Earth, the Earth's radius, the Earth periods. And so all these are, standard value. The radius of the Earth is pretty well known. The period of the Earth is just like 24 hours. Change that to seconds to be SI units. So you got that. So we've done that. Now, the second part says that if the acceleration now becomes 9.8 instead of whatever value that you calculate, if this is 9.8, what would the period have to be? Okay. So in that case, how fast? In other words, how fast would the Earth have to rotate in order to produce the acceleration that's 9.8? So this basically, we're just going to backtrack. Okay, so from this equation, your A value now is given. Your radius, the radius of the Earth is still does not change. So you can actually calculate the velocity. So you have your A that's equal to V squared over R. Now your V squared is equal to AR, and 9.8 times this magnitude, 6.3. 7 times 10 to the 6, so you can calculate the velocity. The velocity, and I don't have that value, whatever velocity that you have, and then plug into this equation. So your period is basically equal to 2 pi r. So okay, so let me just actually copy it down. 2 pi r over your v, and your v here is square root of 9.8 times this value. So after you do the calculations, you will find that your period is about 5,065 seconds. So in tens of minutes, you should get 84.4 minutes. So you can see that this is when if you are going to generate the centripetal acceleration that has a magnitude 9.8, the Earth has to have a period that's that's 84.4. So in other words, for every 84.4 minutes, it's going to complete a one revolution. As opposed, what we have here now is that it takes about 24 hours to complete one revolution. Okay, so this is that. And the last problem that we want to do is problem 117. All right, so a football player punts the football so that it will have a hand time of flight of 4.5 seconds. So time is given, that's 4.5 seconds. and land 46 meters away, so horizontal distance is given. And if the ball leaves the player's foot 150 centimeters above the ground, so initial height is at 1.5 meters because 150 centimeters, that's 1.5 meters above the ground. What must be the magnitude and angle of the ball's initial velocity with respect to the horizontal? So let's draw the diagram. So you have, let's say 1.5, so maybe, okay, initial height. So this is a diagram. So this is the football, field, and the football players, let's say it's at the ball, the release point from this height to that height is 1.5. So let's say, so we define this to be 0, and here the initial height is located at 1.5 meters. Okay? And it's going to undergo the trajectory like that, and you're asked to find the initial velocity. Okay, we don't know what that is, and the angle is also not given. We don't know. So initial velocity for this instance are not given. The angle and the speed are not given, but you're given the vertical separation. You're also given the horizontal separation. So the horizontal separation is 46 meters. You're also given the time. So in that case, what would be, how do we go about doing this problem? So although this is not given, they are going to be used. So you need to just use the symbol and then and then keep the symbol. So again, no horizontal acceleration, vertical, that's negative g. And so you have your VI. So your VIX should be your VI and then cosine theta. Again, we don't have VI, we don't have theta, but keep it like that. And you have VIX, which is VI and then sine theta. So then, how do we utilize the information we're given to find out your VI and also the theta? You have the vertical separation, you have the horizontal separation, and you have the time. So it's actually quite straightforward because you have the final position is equal to initial position, and then plus initial velocity in the horizontal direction times time. So you can see that we can immediately calculate the horizontal component of the initial velocity. The final position 46, initial position 0. This we do not know, and then time is 4.5. So your VIX, the x component has a value that is 10.2 meter per second. Okay, so we have one component that does not give. That's not sufficient enough to deduce your VI nor the angle. So we need to utilize the information from the vertical separation. So the vertical separation, you have the final position is equal to initial position plus initial velocity times time minus 1/2 gt squared. So let's see what we can get out of it. So final position, this is when it's landing on the ground, is 0. Initial position is 1.5. Initial velocity in the vertical direction, we do not know. The time is 4.5 seconds minus 1/2 times 9.8 and then times 4.5 seconds squared. So you can see that the only variable from this equation would just be this. So you can plug in a number and you can find out your VIY. So your VIY is equal to 21.72 meter per second. So once you have your x component and the y component, then it becomes very straightforward to calculate the initial velocity because your VI is just equal to VIX squared plus VIY squared. You have VIX square it, VIY square it, and then take the square root of sun, so you should have your VI that is equal to 24 meter per second. So that is the speed of the ball. What about angle? You have the x and y component, and this is in reference to the positive x-axis, so you can just use the tangent theta. So tangent theta here is the opposite, which is the y component, over the adjacent, which is the x component. So the y component is 21.72, and the x component is 10.2. So you should calculate your theta. After you do the calculation, your theta is equal to 64.8 degrees. Okay, so you can see that after you've done so many problems on projectile, you should have some fairly understanding that we only use the two sets of equations of motion, and those equations of motion are sufficient enough for you to do any problems, to be honest. So you just have to draw the diagram, lay out the symbol, associate the number with the symbols, and then just use and pick the right equation to use from the two sets of equations. Okay. So I'll stop here.